Today we're going to look at geometric sequences, another subset of sequences that have some special properties. So geometric sequences, here are some examples: 2, 6, 18, 54, 162. We are obviously not adding the same thing. Um, we are multiplying in this case. 2 times 3 times 3 times 3 times 3. But we call that, when we're multiplying the same thing, we call that a common ratio. Give it the letter R. In this case, R is 3. 10, 5, 2.5, 1 1/4. One might say we're taking half every time, so dividing by 2. But dividing by 2 is the same thing as multiplying by 1/2. So our common ratio is 1/2. 4, 20, 100, 500. In this case, we're multiplying by 5 every time, so our common ratio is 5. These are geometric sequences, and they are highly connected to exponential functions. Because what happens if something is growing, at some point it tips the balance and starts growing incredibly, right? If I tried to continue this multiplying by 3, I would be taxing my brain power to come up with the next couple of terms. It's also true that if your common ratio is a fraction that's less than 1, you start out losing, and then it starts to get incredibly small, but it never becomes nothing. So you get that look of either exponential growth, yeah, or in this case, exponential decay, right, where we never lose all of it. So it does have an exponential look to it. Exponential functions had the form y equals some starting point. I think we used P for principal, right? And then there was some base value, right? And then it was raised to a power to indicate, going forward. Okay, well, that's going to happen with our geometric sequences. This base number is our common ratio. So we're tripling every time, yeah? Or we're halving every time, or we're quintupling every time. So this is going to look like a sub n is equal to, and I'm going to leave the starting point off for a minute, 3 raised to the, and there are two ways to do this. If you want to get this sequence to appear, some people they like to say that this is their starting amount. Okay, if you want to do that, 2 times 3, then this 2 doesn't have any factors of 3. So you're going to have to say, if it's your first term, you want 1 minus 1, no factors of 3. If it's your second term, you want 2 times 1 factor of 3. If it's your third term, you want 2 factors of 3, right? Because 2 times 3 times another 3. If you want it to be exactly like this, we could call this a sub n is equal to 3 to the n, but then we'd need to know what term came before the first term. That would be our starting point at time 0 rather than at time 1. If I wanted to do that, if I'm multiplying by 3 to go forward, I divide by 3 to go backward. So this would be 2/3. And you have to decide who you are. Do you like it better this way so that your first term appears here? Then you always have to have n minus 1 as your power. If you want to have n as your power, then you have to be willing to think about what term would have come before your first term. So in each case, in this one, this would be a sub n is equal to 10 times 1/2 to the n, or a sub n is equal to, I'm multiplying by 1/2, I would sort of divide by 1/2. So 10 divided by 1/2 is 20 times 1/2 to the n. Both of those are equivalent. In this case, a sub n is equal to, pardon me, 4 times 5 to the n, or a sub n is equal to, I'm multiplying by 5, so I divide by 5, 4/5 times 5. Oh, this was n minus 1. Oops, sorry about that. N. So these have to have n minus 1. If you're going to use the first term, then you're going to use n minus 1 as your power. If you're going to find the 0 term, then you can use n as your power. Probably based on the way that I did this, I tend to do this, although students tend to find this easier because you use the things that you have and know. You just have to remember n minus 1 is the power. And obviously, I don't always remember that. Okay, so what would it be here? A sub n is equal to, 6. You can use 6 times negative 10 to the n minus 1. Or a sub n is equal to, if it's multiplied by negative 10, I divide by negative 10. So 6 divided by negative 10 is negative 3/5 times negative 10 to the n. And let's take a look at what these terms would look like as they started out. It would be like 6 times negative 10, negative 60, times negative 10, 600, times negative 10, negative 6,000, times negative 10, 60,000. So we see that the terms are actually going from positive to negative to positive to negative to positive to negative, because our base is a negative number. Okay. This first term, negative 6 times 10, negative 60, times 10, negative 600, times 10, negative 6,000. Notice that these terms are not alternating back and forth. They're actually all staying negative because my first term was negative and I'm continuously multiplying by something positive. A sub n is equal to negative 6 times 10 to the n minus 1, or a sub n is equal to negative 3/5, right, the term that came before, times 10 to the n. Okay, these terms would be 1 square root of 3, 3, 3 square root of 3, 9, 9 square root of 3, 27, etc. Right? I'm continually multiplying by the square root of 3. A sub n is equal to 1 times the square root of 3 to the n minus 1 power, or a sub n is equal to 1 divided by the square root of 3, so root 3 over 3 times the square root of 3 to the nth power. Okay, that's it.